So we were doing atomic structure, and in last class we discussed about just started this atomic structure, discussed about cathode rays. As I told you that cathode rays were discovered by William Crookes, and we discussed how these cathode rays are produced, and at normal pressure, that is 1 atm, what will be the observation? Nothing will be observed. And if pressure is 0.01 atm, then gas emits, and color of light depends upon the nature of the gas. And at 10 to the power minus 4 atm pressure, walls of discharge tube opposite to cathode rays starts glowing. So this all we have done. This all we have done. So now we'll be doing the next. We discussed even about properties also, properties of cathode rays, and who studied those properties of cathode rays. It was Sir J.J. Thomson who discovered actually electron. So there in this cathode ray discharge tube experiment only, he discovered electrons. So we discussed this all already there in our previous class, and we discussed about anode rays also, and now we'll be talking about nature of radiations. Now we'll be talking about nature of radiations. So in this nature of radiation, is it PowerPoint presentation is visible, Mesha? Is it visible?
Yes, sir.
PowerPoint presentation?
Yes, sir.
What it is written there on the screen?
The nature of radiation according to Koskula theory of light.
Oh, fine. Okay, fine. So instead of I'll share another screen now. Now what it is seen there on the screen? Atomic structure, nature of radiations.
Yes, sir.
Only that?
Yes, sir.
Now what next is?
So according to Koskula theory of light, Newton.
Okay, fine. So this is what our topic is: atomic structure, nature of radiations. Today we'll be talking about this. So in this first, this is more related to physics. Okay, chemistry do not starts from here, but since I want to explain this nature of radiation completely, so here I'll be talking about Newton's corpuscular theory of light also, but that falls under physics only. This nature of radiation will be there in physics also. So according to corpuscular theory of light, which was given by Newton, light is a stream of particles. This corpuscular theory of light can explain reflection and refraction. You know reflection, and you know refraction also, that is there in physics light. So reflection and refraction could be explained with the help of this corpuscular theory of light, but this theory is unable to explain interference and diffraction. I'll let you know what the meaning of interference and diffraction is. Fine. So this corpuscular theory, which was given by Newton, tells us that light is a stream of particles. This corpuscular theory of light can explain reflection and refraction of light but failed to explain interference and diffraction. Fine. What next to this corpuscular theory of light is? Next is wave theory of radiations. We are talking about nature of radiations now. So different theories were given to explain this nature of radiation. First was Newton's corpuscular theory, and then second is wave theory of radiation. According to this wave theory of radiation, radiation travels in the form of radiation travels in the form of radiation travels in the form of wave. Radiation travels in the form of wave. Thrust and trough. This is thrust and this is trough. Fine. So radiation travels in the form of wave. That is wave theory of radiation. This distance from here to here, that is wavelength, and this height is called amplitude, and this is propagation velocity. This is propagation velocity. So light travels in the form of wave. This could explain interference and diffraction. I'll let you know that what diffraction and interference is. That will be there in the fourth screen. Fine. So that we'll be talking there only. So radiation travels in this wave theory. It was very difficult for me to remember who gave wave theory of radiation and who gave quantum theory of radiation. Both are Max. Wave theory of radiation is given by Maxwell. Wave theory of radiation is given by Maxwell, and wave theory of radiation is given by Maxwell. Wave theory of radiation is given by Maxwell. Wave theory, Maxwell. And quantum theory was given by Max Planck. So see how you can remember W. Wave theory was given by Maxwell, and quantum theory of radiation was given by Max Planck. So radiation travels in the form of wave, and this wave theory of radiation can explain interference and diffraction, but unable to explain photoelectric effect and black body radiation. Fine. See, in previous what have you said? In previous slide, this could explain reflection and refraction, but failed to explain interference and diffraction. So you gave the next theory. This could explain interference and diffraction, but unable to explain photoelectric effect and black body radiation. This shows that radiations can interfere, are delocalized, and have continuity. See, one wave can interfere another wave. That is what the meaning of interference is. One wave can superimpose another wave. One wave is going there in this direction, another wave is going there in this direction. So waves can interfere, and waves do not have any fixed position. See, the position of chair is certain. Position of table is certain, means localized.
Yes, sir.
Localized. Fine. So position of particle is localized, but position of wave is delocalized. It means waves do not have any fixed position. Waves do not have any fixed position. Waves are delocalized, and one wave can interfere another wave. And in waves, see, particles will be like this now. But in waves means discontinuity. Continuity is not there in particles. But in waves, continuity is there. So waves are continuous, delocalized, and can interfere. Fine. This question was there in entrance examination. Davison and Germer's experiment confers the wave nature of electron. Wave nature of electron was confirmed by which experiment? Davison and Germer's experiment. So this is about wave theory of radiation. As I told you there in the beginning, corpuscular theory can explain reflection and refraction, but could not explain interference and diffraction. So you gave next theory, that is wave theory of radiation, according to which diffraction and interference could be explained, but photoelectric effect and black body couldn't be. So Davison and Germer's experiment confirms the wave nature of electron. Now the next, interference. See, interference. See, this is one wave. This is one wave. And this is another wave. This is another wave. See, in this direction your car is moving, another car is also moving there in the same direction. That is Doppler's effect now. That is Doppler's effect now. That is Doppler's effect now. That is Doppler's effect.
Yes, sir.
Fine. That is Doppler's effect. This screen is not taking command. I'll reconnect. I'll reconnect. Fine. I'll reconnect. Now, am I audible?
Yes, sir.
Okay, fine. So see, one wave is moving there in this direction and second wave is moving there in opposite direction. Oh, sorry, same direction. So if both cars are moving there in the same direction, then here this will be very clearly observed, na? Very clear vision will be observed. Here everything will be very clean. And suppose, see, one wave is moving there in this direction and second wave is moving there in opposite. One car is moving there in this direction and another car is moving there in this direction. Then here, this will appear blurred now. You won't be able to observe it clearly. In night, it happens now. In night, it happens.
Yes, sir.
If both are using headlights and moving there in the same direction, then this will become clear now. But if both cars are moving there in opposite direction in night, then both are using headlights, then this will become blurred. You won't be able to observe it clearly. So if two waves are moving there in opposite direction, that is called diffraction. And if two waves are moving there in the same direction, then it is called interference. Interference means interaction of two waves and diffraction means formation of light and dark bands. Is it fine?
Sir, formation of light and dark bands, matlab?
Means, see, if two lights are moving there in opposite direction, if two lights are moving there in the opposite direction, then somewhere it will be light band and somewhere it will be dark. If light, then you can see, and if it is dark, then you can't see. Band means strips, regions.
Okay, sir.
If two waves are moving there in the same direction, that is what Doppler effect na? If two trains are moving there in the same direction, and if two trains are moving there in the opposite direction,
Yes, sir.
if they are moving there in opposite direction, then obviously approaching towards each other, then that sound will, frequency of sound increases. But if two are moving away from each other, then the frequency of sound decreases, intensity of sound decreases. Is it okay?
Yes, sir.
Fine. So this is about interference and diffraction. Interference means two waves superimposes each other. That is constructive overlapping. And diffraction two waves opposes each other, means destructive overlapping. This is destructive, resultant will be 0, and here resultant will be maximum. This will be constructive overlapping. So now what have you done? You have said that corpuscular theory of Newton, that is light is a stream of light. This can explain deflection and diffraction, but unable to explain interference and diffraction. And then wave theory of radiation, which was given by Maxwell, according to which light travels in the form of wave. This could explain interference and diffraction, but couldn't explain photoelectric effect and black body radiation. What photoelectric effect and black body radiations are, this we'll discuss laterwards. Fine. In coming topics, this shows that radiation can interfere, are delocalized, and have continuity. Davison and Germer's experiment confirms the wave nature of electron. Here we explained about interference and diffraction. Now, what next is quantum or particle theory of radiation? This was given by Max Planck. Maxwell gave you wave theory of radiation, and Max Planck gave you quantum or particle theory of radiation. According to Max Planck's quantum theory or particle theory of radiation, radiation travels in the form of discrete bundles of, see, I'll tell you here, these are particles. Between particles, gap is there now. But
Yes,
in
sir.
waves, there is no gap. But in waves, there is no gap. So waves are continuous, but particles are discontinuous. Without suppose delocating this particle, without dislocating this particle can't move from this place to this place now. Means particles are localized. Particles are localized. Without dislocating this particle from their position, this particle can't move this place to this place now. What does it mean? Means particles have orientation. Particles are localized. They have fixed position, while waves are delocalized. Without dislocating this particle can't move to this place now, means particles can't interfere. But without disturbing another wave, one wave can pass through it now, means waves can interfere. Waves are continuous. Waves are continuous. Waves are continuous. Waves can interfere, and waves are delocalized. While in particles, what we will write? Discontinuous. Particles are discontinuous. Then particles can't interfere. And particles are localized. Particles are localized. So these are three diagrams in which particles, waves, and waves are shown here. Fine. In this way, that is what you wrote here now, delocalized, interference, and continuity. So this is what you can explain it here. So radiation travels in the form of discrete bundles of energy called quanta. This could explain photoelectric effect and black body radiations. So now this problem is also over, because this wave theory of radiation was unable to explain photoelectric effect and black body radiation, but this quantum or particle theory of radiation can explain photoelectric effect and black body radiation. Fine. This shows that radiations can't interfere, are localized, and have discontinuity. Particle shows that radiations can't interfere, are localized, and have discontinuity. That is what I explained you here. Discontinuous, can't interfere, and localized. So that's what it is written here. Now see, these are the questions which they previously asked. The first use of quantum theory to explain the structure of atom was made by Bohr. Bohr was the first person who used this quantum theory to explain the structure of atom. Quantum theory of radiation was used by Einstein to explain photoelectric effect. To explain, these are all questions, to explain photoelectric effect, Einstein used this quantum theory of radiation. Scintillation method and photoelectric effect confirms the particle nature of electron. See, this question is here, and there it was Davison and Germer's experiment, and here it is scintillation method and photoelectric effect, which confirms the particle nature of electron. So you should be very, very careful there in all these things. All these are questions. All these are questions which they asked in previous years. Now see, one is saying, Maxwell is saying radiation shows, Maxwell is saying that radiation shows wave nature. And Planck is saying, Max Planck is saying that radiation shows particle nature. So who is true? We don't know. This could explain this could explain interference and diffraction, but could not explain photoelectric effect and black body radiation. This can explain photoelectric effect and black body radiation. Fine. So now who is right one? So what they said, de Broglie said that both are right. Radiation travels in the form of wave as well as in the form of particles. De Broglie said that radiation travels in the form of wave as well as in the form of particles too. Means radiation show dual nature. Radiation shows dual nature. Radiation shows dual nature. Later words, I'll rectify this too. Whether it is nature of radiation or nature of matter, I'll rectify that too. But here, what you should write, de Broglie's dual nature of radiation. So de Broglie stated that radiation travels in the form of wave as well as in the form of particles. So he made this Maxwell and Max Planck both theories right. He said both are right, both of them are correct. This de Broglie's dual nature of radiation is based on Mulliken's oil droplet experiment. This de Broglie's dual nature of radiation is based on Mulliken's oil droplet experiment, which proves that radiation travels in the form of particle. And diffraction study also that proves that radiation travels in the form of wave. So this de Broglie's dual nature of radiation is based on Mulliken's oil droplet experiment and diffraction study. This shows that it is showing particle nature, and this diffraction study shows that it is having wave nature. Radiation travels in the form of waves as well as in the form of particles. That is what the meaning of dual nature of radiation is. Einstein, see, after graduation, after BSc, what you do? You do MSc. And after MSc, what usually you do? PhD.
The PhD.
No? PhD.
Yes,
Like that. This is in general. But in medical, first you do MBBS. Then what you do next? MD.
then
This is graduation. This is post-graduation, MD.
Yes, sir.
Doctorate in, doctorate in, no, not doctorate in medicine. I'm not sure, master of surgeon, and this is master of, I'm not sure about that. So I won't be. So first, this is graduation, this is post-graduation. Then what next? After post-graduation, what you do there in medical science, medical field? DM. After MD, as in science, after MSc, you do PhD. Like that in medical profession, after MD, what you do? DM. DM is doctorate in medicine. Doctorate in medicine. That is PhD. They are in medical science. So these are professors. This is the most highly qualified medical professional. Fine. So DM. One is DM and second is engineer. Na? Engineer means what? How do you write engineers? ER. For doctors, it is DR. For engineers, it is
Yes,
ER.
sir.
For architects, it is AR. Is it okay? So 2 points are there. One is DM and second is engineer. dm. dm means de Broglie. D stands for de Broglie. De Broglie. De Broglie gave wave nature of matter. Nature of matter, sorry. Nature of matter. And ER. E stands for Einstein. Einstein gave wave nature of radiation. Sorry, nature of radiation. So nature of radiation was given by Einstein and nature of matter was given by de Broglie. But here you wrote de Broglie's dual nature of radiation. Na? So technically it is wrong. Dual nature of radiation was given by Einstein. But here in general we will be writing de Broglie's dual nature of radiation. So that's not the true one. Is it right? This question they asked there in different entrance examinations. That's why I'm stressing a lot on this. Einstein
Okay.
gave nature of radiation, ER. Einstein gave nature of radiation and de Broglie gave nature of matter. So nature of matter and nature of radiations are two different things. One was given by Einstein and second was given by de Broglie. So that is what it is written here. De Broglie proposed the dual nature of matter and Einstein proposed the dual nature of radiation. So radiation, Einstein. Matter, de Broglie. Fine. Einstein proved,
Yes.
okay, fine. Einstein proved the presence of photons in photoelectric effect on the basis of quantum theory of radiation. Einstein proved the presence of photons in photoelectric effect on the basis of quantum theory of radiation. Fine. So this statement also we should remember that Einstein proved the presence of photons on photoelectric effect on the basis of quantum theory of radiation. Now they can ask you on what basis Einstein proved the presence of photons in photoelectric effect. So on the basis of quantum theory of radiation, he proved the presence of photons in photoelectric effect. Or see what Einstein's mass defect equation is. What Einstein's mass defect equation is. Einstein's mass defect equation. E is equal to mc square. And then what is Planck's equation? E is equal to h nu, that is hc upon lambda. So this is also E and this is also E. So mc square is equal to hc upon lambda. So mc is square is equal to hc upon lambda. This c and c will be cancelled. So mc is equal to h upon lambda. M into c, that is mass into velocity. That is mass into velocity. Mass into velocity is momentum. Product of mass and velocity is called momentum. So mc is equal to h upon lambda. mc is equal to h upon lambda. What does it mean? P is equal to h upon lambda. Momentum is equal to Planck's constant upon wavelength. Planck's constant upon wavelength. What is Planck's equation? Planck's equation is equal to E is equal to h nu. What h is? Actually, E is directly proportional to frequency. Energy of the radiation is directly proportional to frequency. If you remove this directly proportional sign, then what you will be doing? You will be putting an equal to sign and then a constant. That is Planck's constant. H is Planck's constant. And this equation is known as Planck's equation. Nu is equal to C upon lambda. So instead of nu, you can write C upon lambda also. So E is equal to hc upon lambda. That is what I wrote here. That's Planck's equation. Now you will equate both of them and C will be cancelled. So mc is equal to h upon lambda, m into c, that is mass into velocity. Product of mass and velocity is called momentum. So momentum is equal to h upon lambda. Now this is what I have done, this all. Now see,
सर
yeah.
आप एक बार और समझा देंगे, समझ नहीं आया।
अच्छा चलिए ठीक है, दोबारा से मैं बता देता हूँ। क्या कहा आपने? एक तो इक्वेशन होता है E इज इक्वल टू, एक तो इक्वेशन होता है E इज इक्वल टू एम सी स्क्वायर, एक तो इक्वेशन होता है E इज इक्वल टू एम सी स्क्वायर, आइंस्टीन का इक्वेशन होता है, ठीक है, आइंस्टीन का इक्वेशन होता है। और दूसरा होता है E इज इक्वल टू एच न्यू, ये प्लैंक्स का इक्वेशन होता है। एक तो आइंस्टीन का इक्वेशन होता है E इज इक्वल टू एम सी स्क्वायर, और दूसरा प्लैंक्स इक्वेशन होता है E इज इक्वल टू एच न्यू। एच क्या होता है? प्लैंक्स कांस्टेंट, न्यू क्या होता है? फ्रीक्वेंसी, और E क्या होता है? एनर्जी, M क्या होता है? मास, और C क्या होता है? वेलोसिटी। So E is equal to h nu and E is equal to mc square. Nu is equal to क्या होता है? C upon lambda. Frequency of light is equal to क्या होता है? Velocity of light upon wavelength of light. तो इस nu की जगह पर C upon lambda लिख दीजिए। तो E is equal to क्या आ गया? hc upon lambda. ये भी E है and this is also E. So equate both of them. mc square is equal to hc upon lambda. C and C will be cancelled out. What we will get? mc is equal to h upon lambda. P is equal to momentum is equal to mass into velocity. So momentum is equal to mass into velocity. So instead of mass and velocity, we will be writing momentum. So P is equal to h upon lambda. Now, is it clear?
Yes, sir.
Fine. Now see, till here it is over. Now gamma is equal to, that is mu is equal to, sorry, C upon h, C upon h upon m, m. So now m v or c, m v or c. So now gamma is equal to mc square upon h. This is another relationship. C, gamma is equal to, C upon lambda. Gamma is equal to C upon lambda. So gamma is equal to C upon lambda. Lambda is equal to h upon mc na. Lambda is equal to, h upon mc na. Lambda is equal to h upon
Yes, sir.
mc. So instead of lambda, what have we written? H upon mc. Now this and c will be placed here. So what we will be writing? Gamma is equal to mc square upon h. Gamma is equal to mc square upon h. C, kinetic energy is equal to half mv square. Kinetic energy is equal to half mv square. So mv square, that is mc square, will be twice kinetic energy. C or v is velocity na. This 2 will be shifted here. So mv square is equal to twice kinetic energy na. Is it okay?
Yes, sir.
So instead of this mc square, what you can write? Twice ke. So nu is equal to twice kinetic energy upon h. Twice kinetic energy upon h. Twice kinetic energy upon h. This is not lambda, it is h. This is not lambda, it is h. Twice kinetic energy upon h. Fine.
Yes, sir.
So this equation is only applicable to microscopic objects. For daily life objects, it won't be applicable. I'll tell you why. What's the reason why it is not applied on daily life objects? It is only applicable to microscopic objects, not applicable to macroscopic objects. That I'll let you know. Fine.
Okay, sir.
So this all is over. Now we'll go to the next one, significance of de Broglie's concept. Is this clear? This is very, very important. Numericals will be there based on this all. Fine, numericals will
Yes,
be there
sir.
based on this all. So you should be having very good clarity on this concept. Then only you can handle. You will get a huge number of questions based on this Einstein's equation or a Planck's equation or de Broglie's relationship. This is de Broglie's relationship. De Broglie gave this relationship now, so it is known as de Broglie's equation or de Broglie's relationship. Now we'll go to the significance of de Broglie's concept. Now we'll go to the significance of de Broglie. See, in French, we write like this, now D is a small, fine, and B is capital. So that's French one. So that's why you have to write like that only. Significance of de Broglie's concept. Now, significance of de Broglie's concept. Significance of de Broglie's concept. Now, what are the significance of de Broglie's concept? Now see, angular momentum in closed orbits are quantized. Angular momentum is MVR. MVR, that is mass into velocity into distance. Mass into velocity into distance. Product of mass, velocity, and distance is called, radii is called angular momentum. That is always quantized, that is h upon 2 pi into n, where n is always 1, 2, 3, 4, 5 like this. It can't be 4.5. It can't be fractional. Fine, will always be a whole number. This is what the meaning of quantized is. Angular momentum in closed orbits are quantized, that is MVR is equal to nh upon 2 pi. MVR is equal to nh upon 2 pi, h upon 2 pi into n. That is the meaning of quantized. The wavelength associated with a moving object is inversely proportional to its mass. See, elephant and horse, which is heavier, elephant or horse?
Elephant.
Elephant. So elephant is heavy now. So distance covered by elephant will be less. That is wavelength. Distance covered means the distance, wavelength means the distance covered by the wave. So which will travel more, elephant or horse?
Horse.
Horse will travel more. Why? Because its mass is less now. So mass is less, so wavelength is more, means distance covered will be more. So that is what it is written here, that wavelength associated with a moving object is inversely proportional to its mass. Wavelength and mass both are inversely proportional. So mass and wavelength are inversely proportional. If mass is large, then wavelength will be very, very less. That's why you have said in the starting that it is only applicable to microscopic objects. So in microscopic objects, mass will be less. So distance traveled will be more and you can observe it easily. But if mass is more, then distance traveled will be less and you won't be able to observe it properly. That's the reason. Is it okay?
Yes, sir.
The same thing I have written here also. As I told you about elephant and horse, here it is given car. Car is also macroscopic object or daily life object. Mass of car is more than an electron. So more the mass, less will be the wavelength. So less distance that car will travel and electron will travel more distance because its mass is less. The wavelength, lambda is wavelength. Wavelength of car is very low. We can't measure it. As in daily life, we come across the macroscopic objects. So de Broglie's relationship has no significance in our daily life. Fine. De Broglie's concept has no significance in our daily life. Fine.
Yes, sir.
Okay. So just take care of this. More mass, less wavelength. Then you won't be able to observe that distance covered by the. Now see Heisenberg's next topic is Heisenberg's uncertainty principle. Now, what next topic is Heisenberg's uncertainty principle. See, according to Heisenberg's uncertainty principle, del x into del p is greater than or equal to h upon 4 pi. Del x into del p is greater than h upon 4 pi. What del x is? Change in position. What del x is? Change in position. What del p is? See here, x is written now, position. X is written here, position. So del x is change in position. Del x is change in position. What del p is? Change in momentum. What del p? P is momentum. So del p is change in momentum. Product of change in position and change in momentum will always be, greater than or equal to h upon 4 pi.
Sir,
Product
what
of
is del P?
del p is change in momentum. See here written up, p is momentum. So del p will be change in momentum. So product of change in position and change in momentum will always be greater than or equal to h equal to ratio of h and 4 pi. Fine. This
Yes, sir.
this is not bookish language. Huh? In bookish language, it is something else. But you should know this also. Na? Product of del x and del p is greater than or equal to h upon 4 pi. Ratio of h and 4 pi. C, what does it stands for? What does it means? This Heisenberg's uncertainty principle. Change in position and change in momentum. Change in position and change in momentum of a microscopic object can't be explained. Change in position and change in momentum of a microscopic object can't be determined simultaneously with certainty. Change in position and change in momentum of a microscopic object can't be determined simultaneously with certainty. Any one you can tell exactly with certainty. Both simultaneously with certainty can't be explained. Any one can be certain, second will be uncertain. Is it okay?
Yes, sir.
Change in, listen once again, obviously it's written this all here too, but change in position and change in momentum of a microscopic particle can't be determined simultaneously with certainty. Two words here are keywords. If you are not writing simultaneously now, then you will be getting 0. If you are not writing certainty, then also you will get 0. If I'll be reading this answer, then I'll be looking for these two words first. If these two words are there, then I'll be reading the complete sentence. Otherwise, I'll be crossing it and will be giving 0. So these two are key words there in this Heisenberg's uncertainty principle. Listen once again. Change in position and change in momentum of a microscopic particle can't be determined simultaneously with certainty. Can't be determined simultaneously with certainty. Both can't be explained with certainty simultaneously. Any one can be certain and second will be uncertain. So this is what the meaning of Heisenberg's uncertainty principle is. P is equal to mc. So del P is equal to m del C. So in place of this del P, we will be writing m del C. So del x into m del C will be greater than or equal to h upon 4 pi. Now out of this all, what you need to calculate? H is constant. H is constant. Planck's constant is 6.625. H is Planck's constant, that is 6.625 into 10 to the power minus 34 joule into second. In one exam, they asked this value of H. They gave 6.625 in 10 to the power minus 34 joule per second. They gave 6.625 in 10 to the power minus 34 joule into second. Like this, all four values were 6.625 in 10 to the power minus 34, but units were different. You should be very particular even in units too, not only exact numerical values, but in units also you must be very particular. So 6.625 in 10 to the power minus 34 joule into second, that's the value of H. And pi is also constant. Pi is also constant. So H is constant, pi is constant, that is 22/7. Now mass, if suppose they will be talking about electron, mass of electron will also be same. and the velocity of electron will be the velocity of light if it is not given. So this is constant, this is constant, this is constant, this is constant. So nothing they will be asking, nothing they will be giving you, and will be asking you change in position of an electron. So change in position of an electron will be del X will be equal to H is 6.625 into 10 to the power minus 34, fine, upon 4 into 3.14 into M is 9.1 into 10 to the power minus 9.1, 9.1 into 9.1 into 10 to the power minus 31 kg, and C is 3 into 10 to the power 8 meter per second. Just to simplify this all, you will get the change in position of an electron. Is this clear? Just to put the values. If still it is not clear, you can ask me
So
all
what
these.
is 9.1 into 10 to the
9.1
power?
is the mass of the electron.
Okay.
9.1 in 10 to the power minus 31 is the mass of the electron in kg. In mole concept we did it now. Fine.
Yes, sir.
So if still you are not getting, you can ask me even in next class too. Fine. So never hesitate to ask all these things. In this way only I'll come to know about your memory problem or whatever it is. Then only I can help you now. So always let me know wherever you are having problems. In this way, your teacher will come to know about your negatives and will help you accordingly. Is this
Yes,
all
sir.
okay? Should I go
Yes,
to the
sir.
next one?
Yes, sir.
Fine. So
Sir,
this
I
is
have a class at 1.
at 1 you are having class. Okay,
Yes, a
fine.
physics class.
So, okay, fine. So just within 2-3 minutes, I'll finish this all. Already it is over. So this was
Yes, sir.
Heisenberg's uncertainty principle. In case of large sized objects, uncertainty in position, I'll explain you this tomorrow. Fine. Otherwise, in this much time, it won't be finished. Fine. I'll explain once
Okay,
again
sir.
this Heisenberg's uncertainty principle. Fine. Okay. Thank you. Thank you very much.
Thank you, sir.
Okay. Fine. Bye.